All right, welcome back. This is 4.4. And it's on absolute extremum. So recall what extremum are. Extrema are maxes and mins. We've done local max or relative. Local or relative maxes and mins. Absolute max. Is kind of like the max of the maxes. If it exists. And absolute min is the minimum of minimums. Also, if it exists. The nice fancy jargon they use for absolute max. You want the math jargon for it. If f of x naught is greater than or equal to all f of x for all x. That's the symbol for all x in the domain of f. Then x naught is an absolute max. F of x naught is the absolute max. It's actually the y value. And absolute min says the same shit. But it changes it to if f of x naught is less than or equal to f of x. Or all x, then f of x naught is the absolute min. So like absolute max is like in the easiest terms, biggest y value. And absolute min is smallest y value. Now, where did we find the maxes and mins before?
Not the inflection point or the graph, which is the highest point the curve.
But how do we find that? First derivative leads us to it, yeah. So we were doing critical points. We found critical points. This is where the slope equals 0. Which meant it either went up to it and then down. Or down and then up. It's been a while, I know it's been a week, and we yellow it tested between them. There are other options for the absolute one though. If there are endpoints. These are options for the absolutes as well.
When you mean that, do you mean like a piecewise function? Like the endpoint of a piecewise line?
Or something that is not an infinite line, like with a restricted domain. I'll do the example, don't worry. These are options for the absolute extrema as well. Let's look at f of x equals x squared on two scenarios here. And we're gonna go on 1 to 3. And we're also gonna look at f of x equals x squared on 1 to 3, but not including the endpoints. So if you graph this, when x equals 1, y equals 1. And when x equals 3, y equals 9. So. This is the highest point on the graph. Absolute max is 9. At x equals 3. Lowest point is at 1. So the absolute min is equal to 1 at x equals 1. Make sense? That's without having any other derivatives in there, but like the endpoints are like what's going on here. It changes when we don't include those endpoints. No matter how close. This is on an open interval. Open intervals are where you don't include the endpoints. It doesn't matter how close I get to 3. Like say 2.99999999. I can always get closer. With more decimals. So like maybe I had 6 9s before. I'll go 7 9s now. We'll make it 8, so it's clear it's different. And which will result in a higher value. Does that make sense? Like if I do 2 we're looking at squares right here. So if I do 2.9 squared. I get 8.41. If I do 2.999 squared. That's 4 nines. I get 9994. If I do 2.9999. Another 9 squared. I'm gonna get a slightly larger number, but it's gonna show up in the decimal places.
Yeah, it's like finding the limit without getting to it.
Yeah, it's like I'm trying to find a limit, but I never actually get to it. There's no max. So there's no. This means there's no max. Or no absolute max there. And also, same thing at x equals 1. No absolute min. I mean, we want to include 1 and 3, but they're not in the domain, so we can't actually evaluate at those points. There's a couple other scenarios that pop up where you'll see different stuff. Like if we have f of x equals 1 minus x squared. From -1 to 1. Just make the graph simple. Absolute max is there. You would find that at the derivative. Absolute max equals 1. Which is not at an endpoint. And the absolute min is 0. And it occurs in 2 spots. Or we could have something like 4x cubed plus 3x squared plus 2x plus 1. I have no idea where these points are on the graph, other than 0, 1 is a point. But I don't know exactly how this looks, but it is gonna go up and it's gonna come down and it's gonna go back up. We have a local max here. We have a local min here, wherever they are, we can find them with the derivatives. But there is no absolute max or min. Because it keeps going downward to the left and it keeps going upward to the right. So this is building on the max and min things and just adding that we might have a cap. We might have a largest, or we might have a smallest. That's all that's really happening in this section, so this section is, if you understood the maxes and mins, this shouldn't be all that difficult. The following is called the extreme value theorem. It just kinda spells out like this shit in a little bit more math jargon. And it actually guarantees an absolute max and min if the following are true. If f of x is continuous on a closed interval. A to B with brackets. Then f of x has both an absolute max and an absolute min on the interval A to B. So things that don't work, like if it's, first off, if it's not or if it's not closed. We already saw this example, if it's on AB, we could have endpoints with no max. So this is continuous but open. This doesn't work. The other scenario sounds weird. Closed. But not continuous. Which means I have an endpoint on the left and an endpoint on the right. But it's not continuous, which means there's a discontinuity in the middle. I could have. A is here, B is here. I could have something doing this, some middle value C. Where it's doing this. And over here, it's doing that. But there is no max or min because this is going to infinity in the middle. It's got a positive infinity and a negative infinity. And the problem is the continuity, it's not continuous. If we can draw it from start to stop though, without lifting our pen. Or pencil. And it has start and stop. There's a max and a min. And it can be as fucked up as we want it to be. It might have a shitload of maxes, local maxes, a shitload of local mins, but at some point. There is a highest max, and at some point there is a lowest min. So options for all of these. Will be any of the points where the slope changes. And on the, if you can actually see the graph, it's a lot easier, but you don't always have it graphed. So critical points. Where f prime of x equals 0. Are options. As well as endpoints. So it's a very short process. First off, find the critical points from the first derivative. Jesus, that still looks like shit. There we go. Give yourself a little bit more room to write, David. Evaluate all critical points and endpoints in f of x, not the derivative, back to the original function. Because that gives us our y value. And find the largest, find biggest and smallest y. Okay, for example, this is much more meaningful with an example. But if you don't understand conceptually what's going on, it's meaningless. All right, let's go with f of x equals 3x to the fifth power minus 5x cubed on -2 to 0. This is a continuous function and it is closed. We are guaranteed to have an absolute max and absolute min. Polynomials are continuous. So that requirement is met and -2, 0 is closed. So what is the first derivative?
X to the fourth. Minus 15x to the second.
And we want to find out where that equals 0. I can factor out a 15x squared. And have x squared minus 1 left. And this is x minus 1 and x plus 1. So setting each equal to 0, x squared equals 0 gives us x equals 0 as an answer. X minus 1 equals 0, so x equals 1 is an answer. And x plus 1 equals 0 says that x equals -1 is an answer. on the interval -2, 0. Only this one works and this one works. Are in the closed interval. So we'll ignore x equals 1. It's outside of our domain. So we'll evaluate f at the endpoints. And f at critical points. -32. 96 minus 40 is -56. F of 0 is 0. F of -1 is 3 times -1 to the fifth. Minus 5 times -1 cubed. This is -3 plus 5 equals 2. So which one has the lowest value? -56, so we have an absolute min. Of -56 at x equals -2. And what's the largest value? 2. We have an absolute max of 2. At x equals -1. It's a straightforward process, it takes a little, you gotta, sometimes it's calculator work doing this shit. Like I would argue, a lot would probably do this top line in the calculator. And maybe even that line in the calculator, hopefully you can do the 0 without using a calculator. These are all x's, so just plugging in 0, zeros everything out. But other than that, it's not really that complex of a problem. What happens when we don't have a closed interval? So let's say the domain is -infinity to infinity. But continuous. We don't want any asymptotes in the middle here. Because asymptotes will fuck things up, like will change the argument I'm about to make. So when this happens, look at end behavior. Limit as x goes to positive infinity, limit as x goes to negative infinity. You will have two sorts of outcomes here. In general. Generally, if it's continuous but infinite domain, it's usually a polynomial. So this is usually, that's worth stating, usually a polynomial. I can't think of any other well. There are other functions. An exponential, e to the x has an infinite domain. But there are ones, but a lot of ones you'll see here are this. Look at end behavior, we'll look at e to the x in a second. But like if the largest degree is even. Like say x to the fourth plus a bunch of shit. Let's say ax to the fourth. Plus a bunch of stuff. X to the fourth, ax to the fourth is gonna do some shit like this. And if a is negative. It's gonna do some shit like this. And this is gonna happen with any even degree. You'll just have more turning points. These, the critical points. Is n minus one, where n. The amount of them, n is the degree. We can have that many critical points. Or turning points. So I had x to the fourth, there's three, but if we do the limit on this one. Limit as x goes to negative infinity of f of x. Is actually the same as limit as x goes to positive infinity of f of x. It's infinity. So there's no absolute max. But there is. An absolute min. And then on this one. Do the same thing. Limit as x goes to negative infinity of f of x. And limit as x goes to positive infinity of f of x. Both are negative infinity. So there's no min here. But there is an absolute max.
In this case, this works because the end behavior is both going to infinity in the same direction.
Yeah. It's because they're going in the same direction, and it's because it's an even degree.
So if it's not an even degree, then the end behavior would be different though.
Yeah, well, we were gonna about to look at an odd. So largest degree is odd. Ax cubed plus some shit. Other terms. If a is greater than 0. It looks kind of like x cubed, but there's some turning points in the middle. If a is less than 0. It's doing some shit like that. So here there's. On this one, limit as x goes to negative infinity. Is negative. Infinity, and limit as x goes to infinity. Positive infinity is positive infinity. No max nor min. I'm sorry, no absolute max or min. There is a local max and min. And this switches over here. Limit as x goes to negative infinity of f of x is positive infinity. And limit as, that should say negative infinity. And limit as x goes to positive infinity of f of x is negative infinity. Again, no absolute max or min. One's like e to the x or. Recall what u to the x looks like. The x-axis for e to the x is an asymptote. The limit as x goes to infinity here. Of f of x is infinity. The limit as x goes to negative infinity of e to the x. Yeah, I should say negative infinity. Is 0. But. It never equals 0. So e to the x does not have an absolute max or min either. I can always find a value closer to 0 if I take a more negative number for x. And we should do one more example. Because a lot of this is just doing stuff we've done before, but. It's worth locking in. Let's do g of x is. I don't know, x plus 1 over x squared plus 1. And we'll go from 0 to 2. X squared plus 1 is greater than 0 for all x. So we don't have any. Domain restrictions, other than the 0 to 2. There's no asymptotes. So this should be a continuous function. So what is g prime of x? We have high prime low minus high low prime. Over low squared. High prime is 1 over low. Minus high, which is x plus 1. Over derivative of the bottom, which is 2x. All over x squared plus 1 squared. So what do we have? We have x squared plus 1 minus 2x squared minus 2x on top. Which is negative x squared minus 2x plus 1. And we're going to set that equal to 0. The bottom doesn't play a role. It's always positive. We can multiply through by it. I've got negative x squared minus 2x plus 1 equals 0. I don't know about you, but I hate working with shit that looks like that. So I'm going to multiply this by negative 1. And rewrite this as just the opposite signs. Oh, this is fucking ugly. I know, what do we gotta do? That doesn't factor, so. -2 plus, we're doing a quadratic formula. 2 squared minus 4 times 1 times -1. All over 2 times 1. That is square root of 8/2. Which is -1 plus or minus. Square root of 8 is 2√2. The 2's will cancel, and we got that. So x equals -1 minus square root of 2, and x equals -1 plus square root of 2. What are those values? This is -2.4-ish. And this is approximately 0.4. That's the x side. So on 0 to 2. Only this one's inside of it. So we need to check. G of 0. G of -1 plus square root of 2. And G of 2. G of 0 is 1/1, which is 1. G of 2 is 2 plus 1 over 2 squared plus 1. 3/5. This one's gonna be fucking ugly. -1 plus square root of 2 plus 1 over -1 plus square root of 2 squared plus 1. So I still have this in the calculator. I'm gonna do this one. We will answer squared plus 1. And then I will say square root of 2 divided by the answer. And I'm getting G of that equals approximately 1.207. If anyone else did that. -1 and +1 cancel. You got it? Okay, so we have, where's the absolute max at?
Next term, so. 1.2.
At the shitty one, right? I'm gonna say it's square root of 2, I'm gonna give the complete value. And then I'll say approximately 1.207 at x equals -1 plus square root of 2. And what is the absolute min? 3/5. And that one we can give an exact value for 0.6 at x equals 2. And that will be all for today. You're not gonna like Monday. Monday's word problem day. Tuesday. Maybe you love Monday. What do you have on Monday? Yeah, Tuesday we're doing, well, Tuesday is word problem day, but it's like, let's make this shit useful. Like, let's put calculus to use and, like, it's one of my favorite sections, but a lot of students don't like it because it's word problems. But it actually applies real life.